The speaker of the current session, Dr. Debasmita Panda madam. Dr. Debasmita Panda ma'am completed her MTech in Energy Science and Engineering from IIT Bombay and PhD from IIT Kanpur. Her employment experiences include working as an energy analytic in State Regulatory Commission in India, and she also worked as an engineer at OSC India. Presently, she is working as an assistant professor at NIT Warangal. Her area of research interest includes smart grid planning and operation, management of distributed and flexible energy resources in smart energy system, market concepts for smart grids, and transactive energy market. She has won Best Paper Award at IEEE Conference Bangalore, India in year 2017. She has authored 4 book chapters and peer-reviewed many journals. She also serves as a reviewer to many international journals like Electrical Power System Research Journal, elsewhere, Journal of Emerging Electric and Power System, and also being technical committee and members of many international conference. She is a member of IEEE, member of Power and Energy Society, member of Solar Energy Society of India. Over to you, ma'am, and welcome to the session.
Right, so we have to work as a team. And the rule is that whenever we try to achieve the goal, we plan it, right? So what is our planning? So the planning, the end goal is that we have to reach there to modeling of the MPC. To reach there, we will achieve, we cannot directly jump there, right? We have to stage by stage understand. So we will plan for next 8 hours, from here 8 hours or 6 hours or 5 hours till 5 o'clock or 6 o'clock in the evening. We will plan for the next 8 hours, but execute the plan in each 1 hour, isn't it? So after 1 hour, we will see how much is our progress. Then after 1 hour, depending on the current state where we are in, like what is our understanding level, how much we have covered related to the concept, designing of it, again we will at 1 o'clock, we will again plan for next 8 hours. So window of 8 hours is fixed, and every hour we are going to modify that strategy that we are going to take to achieve the objective. Are you understanding? So I'll be using the notepad in between. Yeah. So we said that the day is beginning at 10 o'clock. Oh, sorry. So day begins, but now it is, thought that it will 10 o'clock, now it is being 12 o'clock, which is not in our control. So that is what the MPC is going to do, that which is not in our control, we are trying to optimize it. So we are beginning at 12 noon, and what is our objective? Objective is to understand, then model or design the controller, and we will validate it with some case study, right? Now what is the rule of the game, as I said? What should be the strategy that we are going to make? One is that we have to work as a team, and at every 1 hour we have to plan for the next 8 hours, 6 hours, 7 hours, depending on how long we'll take, but in whenever we plan, we fix it for the whole day, right? So let us say it is 8 hours. So we always plan for next 8 hours of work. But implement, but the implementation is for how long? Implementation is for 1 hour, because after 1 hour again we are going to re-evaluate at which state we are in, and then we are going to plan for the next 8 hours. Okay? And repeat this process at every hour till we achieve the objective. Fine? Now, in between what happens? So first when we do, we divide the task. Let us first model it, then design it, then simulate it, then implement it. We are dividing. So let us first understand, then model it. While doing this, completing this task, there may be some undesired situation happen. What are the undesired situation that can happen? That is what? What could be the disturbance? That event will not disturb our hall. The disturbance that may be because now we are a team, right? We are working as a team, we have a certain time constraint. But the disturbance that can happen is that somebody in between got some urgent call to leave the team, right? So we have assigned some task to that person. Now that person leave the team. Then is it not going to affect your process of reaching that 8 hours window or that achieving towards the goal? Yes, right? So in between I can have different variables that may affect the process of achieving towards the goal, which is not in our control, which we'll call in MPC term as manipulated variables. Manipulated variables. Right? So what are these? These manipulated variable are nothing but if somebody leaves in between, or like if somebody is not working, he is inside the team but he is not working towards achieving the goal, like he is not helping you in modeling or understanding the problem. So that's something that is beyond our control. So those are called manipulated variables in MPC. Okay? Now, what is the limitation that we are having? So this is something we will be frequently using in MPC, manipulated variables. What are the limitations? Limitation is our ability to understand, or our technical knowledge to understand, or basics that we are having to understand the concept. I cannot make somebody from HSS department sit here and trying to teach him MPC. Isn't it? Is it possible? No. And some people have already background knowledge of MPC, they can catch the concept faster, they can implement it faster. Somebody who doesn't have, even if he is from a technical background, he doesn't have proper exposure towards the MPC, so he may take a little longer time. So the limitation of individual member in the team is something that is going to affect your reaching towards the goal, right? So that is called constraints in MPC. So that means a variable I can vary from some minimum to maximum, like everybody is having a minimum knowledge up to a maximum knowledge related to the concept. So if you have, and how early you catch the concept of MPC and implement it is something, it is in the control of yours, it is not in the control of the overall team, right? So that is called the constraint of a problem. Okay, so the limitation are, and not only your understanding concept, knowing the software, knowing the hardware component that is involved in the modeling is something that may not be there with everyone, right? So that means you are constrained towards implementing the goal in that particular given time horizon which is being given to you, right? So these are the constraints. So limitation is that ability to understand the problem, and also knowledge about, or skills about, we can say skills of the hardware and software that is involved in learning this. So these are called as constraints. Now this constraint can be hard or can be soft. Okay, hard is somebody who doesn't know anything about MPC. Soft can be for someone which is already have little bit information, he can catch it faster. So some constraints are very hard, like some are very much strictly bounded and some are free, right? So that is called constraint in MPC. This is also another term that we are going to use in MPC very much. And our goal is nothing but the objective function that we are trying to solve to achieve, right? So as I said, we started with 12 o'clock. Let us say this is our time horizon. We started at 12 o'clock and we are fixing a time window of 8 hours to understand it. And the rule of the game is what? We have to recalculate after every 1 hour. So this is where we are starting, and this is where we are checking what is our progress, and we are again going to recalculate for another 8 hours. So this is the window that we are calculating right now. Then after another 1 hour, then again we are recalculating the same window after 1 hour. So this in MPC term we call it as receding horizon, or we call it as moving horizon, right? Till we achieve the desired objective. Till we achieve the desired objective. Okay? Is this clear till now, whatever? So, now the three key element that we require for the planning is what? After all this discussion, can you tell me what are the three key elements that we require for the planning?
Defining desired objective.
Exactly. So predicting what is the exact objective that we want to achieve, the exact goal. That means we need to model the plant properly so that we can achieve it faster without moving and second one, tell me, I am not going to spill the beans, yeah? Exactly. So based on our current state and our constraint, hard and soft constraint, how we are going to achieve the objective. So these are the three key elements. And what are the things that we need to keep in mind? That we have to work as a team and we have to maintain that 8 hour of horizon towards achieving the objective. Now, so in MPC, let us try to understand from another example. So this is one of the example. I am going to repeat this example again and again till you understand the modeling of the MPC. Another example let us take is, I'll come to the slides. This is a very famous example of MPC where we can get from anywhere. So I have also took it from the internet. So what you see here, let us say you are driving this car, you are here, okay, and there is a truck going in front of you, and you want to overtake the truck because it is a highway, only the truck is maybe obstacle for you, you want to take a turn from the truck. So initially you calculated the position of the truck, the speed of the truck, and you decided that the red trajectory is that I need to follow to cross the truck, okay. But later when you reached maybe let us say here, you will recalculate. Is it that once you have calculated at this position 1, and you will suddenly take the right turn, that red path? No, right? You are going to recalculate again at this point, again at this point, again at this point, at every instant of time that you are moving ahead, you are going to recalculate which could be the safest path to take to cross the truck, right? And after you reach here, you may be you may be seeing that there is a downhill or sloping is there. Okay, so when there is a sloping in the path, the truck speed will obviously increase, right? If the truck speed is increased, if I am going to the same trajectory, the truck might have reached this position till I take this red path. So instead of going like this, you recalculated and you have moved, or you have taken the green path, right? So this is where the MPC is coming. But now you can say this can be done by a normal PID controller. So I will check the position of the truck and I will take that as a feedback control towards the controller that is there in the car, and I'll take the green path. Is it that a PID controller can do, or is it that only one state that you are seeing for the truck, that is the speed of it or the position of it? No. So how many states you are seeing to decide that I have to take the green path? You are checking the position of the truck, which a normal PID controller also does. You are checking the speed of the truck. You are also checking your steering wheel constraint. How much minimum or how much maximum I can turn left or right. If certain unplanned situation that has happened. So can you tell me now what is the plant here, what is the manipulated variable here, what are the constraint here? Because whatever example we are trying to discuss here, we will try to connect with all the terms of the MPC that we will be using in modeling. So what is our objective here? To overtake the truck, okay? With safely, not that we will overtake the truck by bombarding it, right? We will safely overtake the truck. Next is what? Constraint. What would be the constraint? Exactly, the distance. Yes, very good. So we will be checking the position of the truck, the distance that you are from the truck position currently, and also you will recalculate it till the time you are crossing the truck. At every instant of time, you are recalculating it. That is what is called residing horizon. So at every instant of time, I am recalculating the position of the truck, the speed of the truck, and accordingly deciding that which path to be taken. So what are the different manipulated variables here? Steering, accelerator. So these are the manipulated variable. Which one is the plant here? Can you tell me? Because these are the input I am giving to the plant, and output is crossing the vehicle safely. So as I say, any controller will give a input, we will have an output, and we will have some disturbances. And this output I am taking it as a feedback to the controller to decide what could be the desired input to the plant. So where is the plant here? The car, the vehicle. Our car is our plant. So we are giving this input, we are recalculating in our mind and giving this input to the car. So plant is our car model here, right? And we are trying to achieve the desired control objective, right? So this is another example of MPC. We will take another example from the chess. So here, let us say controller is you. So this is the player 1, that is you, and this is your opponent player, right? So now your move, when you try to move your any of your whatever you can say piece over the chessboard, you will always think that because of my move, what could be the opponent move? And you not only think that, you also think if the opponent move is like this, what could be the further my move? Isn't it? So you will recalculate 5 steps further before you take your first move. Isn't it? And at every instant of time, is it going to remain constant? Whatever you have thought in your mind for the first 5 move, is it going to remain constant? No. It is going to vary depending on the opponent moves. If the opponent moves in a different way, now I will recalculate what we have calculated again, maybe in a very different manner. Isn't it? So every input that we are giving, it is based on the output that we are getting from the opposite side. Till we achieve the desired objective. What is our desired objective? To win the game. Right? So now who is the plant here? The chessboard is the plant here. What are the different manipulated variables? Pieces? The strategy to move, or you can say the opponent strategies and also your strategy. If you take a wrong turn means, or a wrong step, there you can lose the game, right? So this is how the model predictive control work. So it doesn't only take the current output state of the system, it also considered the different manipulated variable as well as what you can say disturbances that present which is beyond its control in order to give a control signal to the controller and to the plant to achieve the desired objective. And as I said, because now you can see I can have many manipulated variable, I cannot have a single variable, but in case of a PID controller, the variable is mostly a single variable, but we can handle multiple variable in MPC, and it is an optimization based algorithm. We are optimizing towards achieving the objective with a set of constraint. So it has the ability to handle the constraint. It allows the current time slot to optimize, and it has the ability to anticipate the future events also. So this is a simplified block diagram of the MPC. If you can see here, from the sensors, you can consider the car here. In that case, the car sensor is going to give you the output measurements, and this output measurement I will give it to the real-time server or solver along with a set of reference outputs, and inside the MPC I will with a set of constraint and all, I will get the what you can say desired control signal to the controller and then to the plant in order to achieve the desired objective. So this is how the MPC works. I can have measured disturbance, manipulated variables, some unmeasured disturbance which is not in our control, and output is measured output, unmeasured output. There can be some unmeasured output. If there is an unmeasured output, what we'll do? If there is a measured output, it is okay. If there is an unmeasured output, what do you mean by an unmeasured output? That can have unknown disturbance, but that is the output, right?
Sensor, we are not planning for any sensor to measure it or something like that. Maybe they are not much significant for the process.
Okay. Okay, fine. So as you can see, it's not that we don't have significance. This unmeasured output that we are getting, maybe some way in the other is affecting your required output, but we are not measuring it. Like we are not getting the exact state of it. Then in that case, we use state estimator to estimate the state because of this unmeasured output, and again we use it as a input, a feedback input to the plant in order to get the desired output. So sometimes some outputs are not directly related to the state of the, now in case of a car movement or truck movement, we say the state of the or the state variable of this model is the position of the truck, right? But in that case, the position of there can be some unmeasured output in case of the speed. But speed we are not measuring for the truck. Let us say it is an unmeasured output. But from the speed, I can also evaluate what could be the position of the truck relative to my position. Isn't it? So how we will use this unmeasured speed of that truck to calculate the state that is useful for us to achieve the objective is what we are going to estimate using a state estimator. So in case we use a state estimator here to what you can say change the unmeasured output into to our desired input, like desired output, giving it as a feedback signal, as a disturbance or any kind of not disturbance, to recalculate the measured towards achieving the measured output. As I said, the speed we are not directly measuring, but we can use the speed information to calculate the state of the vehicle position, right? So that is called a unmeasured output. Like sometimes in power system, if I see from the perspective of the power system, the states of a power system are the voltage and angle, right? But somewhere if there is no meter at a bus, I am not able to measure the voltage at a bus. I can certainly use the power flow equations to calculate the voltage at a bus, because I know that how the voltage and measurements are related, like flow measurements are related, right? So that is what this unmeasured output says. So we'll have manipulated variable, disturbance, control variable, measured variable, and states are nothing but this is going to give us the dynamic condition of the system. Its value give us the dynamic condition of the system, and based on the states only we will try to control the output. So popularity of the MPC, as I said, at every time instant I am going to recalculate the position. So it is a discrete time control, which is like very much required in real time application. At every time instant I am going to recalculate. It is a model based approach, and it predicts the future behavior, optimization based approach, easily handle control, and naturally a MIMO system. So generally we use two terms, CISO and MIMO. What is CISO? Single input, single output system, and MIMO is multiple input, multiple output system. So MPC is able to handle this MIMO. For this we can use a simple PID controller also. And residing horizon approach after the feedback update. We will, okay, so as I said, feedback control, feed forward also, we will see. So we will be, so after I complete, I'll just tell you how to formulate the objective function of a MPC and all. With that we will complete today's session, because at 1 o'clock you are having a lunch break. We will continue this, provided in the next session, whenever I am going to take, I want all of you to have your laptop, and you are having laptops of your own with MATLAB installed in it. Okay, because today I'll only give you a brief overview of the MPC, but in the next class we are going to do a MATLAB hands-on session on modeling a MPC controller. Okay. Okay. So as I said, so these are the different terminologies. Sampling time is that example 8 hours. Sampling time can be 8 hours also. It can be like 1 hour. In our case, it is 1 hour. Time horizon is 8 hours. Prediction horizon. Tell me from the example of that 1 day plan that we are discussing, prediction horizon is 8 hours, okay. Control horizon? Tell me, control. For the duration of the course. So you are saying that my prediction horizon can be greater than the control horizon? Is it that you are trying to say? Exactly, that is what. So prediction horizon can be longer, but control horizon is lesser than that. So it can be less than equals to also. It can be equals to 8 hours also, but this is how it is. Anyways, these are the basic concept that we have already discussed. Any manipulated variable that we are taking it as u of k in throughout this course, and we will write the objective function to minimize the sum of the error error means from the expected value to the predicted value. We are going to minimize the error, square of the error. Then we will have the equality and inequality constraint, and we will calculate the state variables. Yeah. So you can see here, what is the u here? This side, whatever you are seeing is the input, and this is the output. And whatever you are seeing to the left hand side is the past action that has already taken. Whatever you are seeing here is the future that you are going to simulate in order to achieve the target. And where is our target? This is our set point or the target. Okay. So let us say for this input, for these values of the input, when I say input, it is input to the plant. For this set of input, our output was this. Okay. Then we are now at the kth time stamp. This is our current position. Now from the current position, so because we have started from k minus 1, k minus 2 and k minus 3, at kth position we are trying to recalculate for the next predicted period what could be our best control strategy to achieve the target. And where is our target? Here is our target. Okay. So for this set of input, when the input is here, the output is this one. When I am giving input this, the output is this one. For this input, this is the output. For this input, this is the output. So at every instant of time, what we are trying to do, you can see here, from this is of my set point. So from the set point, if I calculate my current state, this will give me my error, isn't it? From the next instant of time, I am taking the information from my past behavior and again moving to the next step. This, let us say this is E1, this is E2, and if you can see, stepwise I am reducing the error till I achieve the set point. E1, E2, E3, E4, E5 up to the same figure here. Up to I achieve the, let us say there are EP predicted steps are there. So I am going to minimize the error till I reach the target set point, isn't it? So how do we mathematically model it? Exactly. So summation over, very good. So we are trying to minimize the error, and this error I can write minimization summation over, let us say this is k equals to 1 to p, because p is my prediction horizon, that is the total 8 hours. I am trying to do E1 square plus E2 square plus E3 square. And what is the E? Up to EP square. So this is up to plus EP square. I am trying to minimize, sorry, EP square, right? What is the E here? Error, but how can I mathematically? I cannot write E1, E2, E3. I am calculating this E from something from here by inferring something from here. What is the E here? My current position and the target. The difference between the current position and the target. What is my current position? Like in case of a truck trajectory, everything you can analyze from analogy from the 3 examples that we have discussed. for achieving the 8 hours of target of understanding MPC. So at every I am recalculating how much I have understood MPC to model it to achieve the goal. Similarly, for the truck example, at what position I am relative to the truck position so that I can cross it safely. So at every instant of time, I am trying to minimize the error between the set point and my current position so that I can achieve the target. Right? So here, how do I model the error? Tell me, mathematically. So set point minus, why? Because if I do set point minus target, set point my current position, or if I do current position minus set point also doesn't going to change. Why? Because we are squaring the error. Now somebody can tell me why we are squaring the error? Exactly. So if there is any negative error, then I may deviate very much from the target towards achieving the objective of minimization of error. To cancel out that, we are squaring it. Okay. And by squaring it, we are ensuring that minimum is only possible if my error is 0. Then only it is possible. So I can write this as, let us say, u of k plus I is my k plus I, where I is equals to, let us say this is I is equals to 1 to p. So u of k plus I is my current position minus the target set point, which is nothing but what we can say y set point, right? I am just writing set point as p, and we are trying to minimize the square error I is equals to 1 to p. Right? So this is how we can model the objective function. Objective function. Now tell me what would be the constraint, because we said that MPC can handle the constraint also. So what are the constraint here? Exactly. So steering wheel, when we are moving, how much maximum I can turn right, how much maximum turn I can turn left, right? Or in case of your whole day understanding of MPC, that means what is maximum you can capture or gather information and try to implement it in the learning process is something is a constraint within us, right? So here, can you tell me mathematically how I will represent that? In this example, as we, from here only we have inferences this objective function, na? That minimization of this is going to be our objective function, isn't it? So from here only, can you tell me what is going to be my constraint? So now I am writing the constraint of this same problem, because I am going to optimize the objective function such that constraints are satisfied. So one of the constraint is that my u, the control horizon that we have fixed, it should be between some minimum and maximum value that we have told about 8 hours, right? So it is from minimum 0, maximum is 8 hours. So this control horizon, so u could be from, it has a lower bound as well as a upper bound. So u or p? P. So my P is bounded by upper and lower. U is the input. This input, as I said, steering wheel position is also input to the plant. So I can say U can also be from minimum to maximum. So this I can also include that this U can be from a lower bound to a upper bound. So this small u, capital U, don't confuse. So this is nothing but, so when which is in the superscript, it is the upper, like upper limit, or you can write max also, right? What else? Can there be any other constraint? Minimum maximum speed. That is what is your U, because U is my input. Control horizon can also be one of the constraint. What else? There is another important. Position of the vehicle. Position of the vehicle is not a constraint to you. It is a input information. What is a constraint? Sampling time is not also a constraint. Okay. If my vehicle is at, let us say 10 kilometer or 20 kilometer per hour, or maybe let us say 30 kilometer per hour, can I suddenly make it to 150? Can I suddenly turn the vehicle safely from right hand to the left hand? The steps that I am taking towards achieving the objective is also a constraint. The input, delta U, the small change that you are making, that is also, I cannot make it suddenly from maximum to minimum, right? I have to take it in a stepwise manner. Otherwise it is unsafe. So I cannot give some unsafe to a constraint to achieve the objective, right? Unsafe as a constraint to satisfy the objective. So I can say the del U change. So if you can see here, so if you can see here, this, let us say this is the U first position. Now I cannot suddenly go to this point now. I have to go in a stepwise manner how it is drawn here. I can go, suddenly cannot go from here to here. I can suddenly go from here to here. It is not possible. Or it is unsafe. Even if it is possible, it is unsafe. So something is unsafe, I cannot give it as a constraint to my controller. So I can say del U is limited by some lower and also upper limit. And here I am just writing it as a continuous step. Because it is discrete, you can just write k value here. K, because this k position is changing at every instant of time. So you can just put del U of k, U of k, because k position is changing. We are moving from k equals to 1 to k plus 1, k plus 2, k plus 3, like that, right? So I can just give a k function here to make it as a discretize. So this is how the constraint is being modeled for any MPC. So I am talking about the objective function that we said. So plant will use this objective function, getting information from the plant's current status. We will trying to achieve, solve the objective function with the set of constraint to calculate the state that we are going to give as an input to the controller, then to the plant. Not controller, controller will decide this. Controller is nothing but is a combination of the plant and this objective function. So this combination will give a input signal to the plant to give you the desired output. So we are using the plant model. So if you can see here, what is the plant model here? The plant model are nothing but the U and Y values and how they are changing. So the plant model, we will be representing in a state space, we can represent as a state space model. That state space model, we will take it as a reference point. From there, we will solve the objective function with a set of constraint that will form your MPC controller. That controller will give signal, will calculate what could be the optimal states, and that states will give it to the plant for achieving the required states. Okay, so that is how a model predictive control work. In PID controller, it is not the case. PID controller will only take the current state of the system. It will have a desired set point. It will calculate the error and it will try to minimize the error and give you the desired output, which is not the case for all problem. Okay. So now how we write the state space model? We write the state space model in this way, where what is the x here? X is the states of the system. So k plus 1 is nothing but the further state of the system from the current state xk. And what is uk here? Input to the controller. Output equation is not written here, but output is y of k will be equals to c of xk and d of uk. So I can write that here also, but anyways, this we will be doing it in more detailed way. So what are the A, B, C, D here, or A, B and all, what are those? These are the system matrices that we will calculate from the plant model. We will use the plant mathematical model and calculate this A, B and C, D, and these are the plant matrices that relate the input with the states and the output. Okay, so that we will see in maybe in the next class while modeling through MATLAB. So here we will close today's session, and we will continue in the next class. I'll tell you what is exactly going to be the next class, because today afternoon we are having MPC from another faculty, which already we have scheduled. My session I'll communicate to you later. But please be installed MATLAB, preferably 2020 onwards, and while implementing, install MPC control toolbox. MPC control toolbox. The vehicle is something related with the speed.
From measured output, it will measure.
Exactly, it will measure the state. So we will estimate it. It may not be the actual one, but it will give you the most accurate estimation of the states. Yeah.
With the help of plant model.
Exactly. Anything? Y of k equals to yk plus I minus. Acha, okay, you are talking about the state space model?
No, you have the impulse response, given the output of the impulse of
Okay, so if you want to write it that.
I can copy it.
Okay, fine. Don't worry, sir. I'll share the PPTs for your convenience. No problem. For the time being, you can write. Yeah, Sabas, you can just guide them.
Thank you, ma'am, for your valuable session. We are looking forward for your another session. So now we'll have lunch, but before that, I would request all the participants to make a signature in this attendance sheet. Right? There are some details unfilled here, right? Like university name, like affiliation, and email ID and mobile number. If they are filled, it's okay. If they're not filled, I would request you to please make it handwritten. Thank you. I'll guide you to the lunch venue. Okay, now after the signatures are done. Thank you.